Hello and welcome to another session of our DE-CIX Academy. I'm Apurva Todkar and today we are going to talk about BGP. That is the foundation of our internet routing. So in today's session, we'll explore how routing of the internet works between providers with the focus on the border gateway protocol. And we'll discuss how internet providers, routers communicate with each other and how data packets find their way across the internet. So let's start simply like what is BGP all about? So how do packets find their way across the internet? So how do internet providers, routers actually talk to each other? So understanding this concept is essential to grasp how the internet actually works. So BGP and the internet are all about network prefixes. So a network prefix is similar to an IP address, which you might be familiar with. And an IP address has a host part and a network part, while a prefix includes only the network part without the host part. So the prefix represents the network portion of an IP address, indicating the boundary between the network and the host part, as I said. So, for example, consider a /22 prefix. In this prefix, the boundary between the network and the host parts is at 22 bits. So, this means that there are 22 bits in the network part and 10 bits in the host part. So, furthermore, you can also subnet this /22 prefix into 4/24 subnets as well. So this flexibility in defining network and host boundaries is a key aspect of how the BGP and the IP addressing works. Let's take another look at the characteristics of the prefix and its notation. So the notation is similar to an IP address, but followed by a slash notation and the number of the bits in the prefix. So like we took the example, for example, this is a /22 prefix and the length of the prefix can range from 0 to 32 bits. So if it's a 32 bit, it represents that it's a single host address and also known as a /32 prefix. So this means that there is no host part and the network part is 32 bits long. So essentially a 32 bit prefix is just a single IP addresses. So an important aspect to understand is that a prefix in a prefix, the host part is always zeros. So in this example, for instance, a /22 prefix, the host part is all zeroed out and the network part is defined by the first 22 bits. Okay, so clearly you can see here that there is a prefix length and how many bits are allocated to the network part and the remaining parts are allocated to the host section. So to summarize, a prefix is written like an IP address with numbers with dotted denotation, but is followed by a slash with a number of bits in the prefix. So this notation clearly defines the boundary between the network part and the host parts. So let's come to a IPv6 prefix. So in IPv6 prefix, the concept is very much the same. There is a network part and a host part, and the prefix length can essentially be of any value. So, however, in IPv6, you typically don't have network smaller than a /64. So, /64 network in an IPv6 is considered as a standard Ethernet network. So, whenever you assign a block to anyone, for example, you have a Google caching or Facebook caching or any of the network that you want to subnet in a /22 in a IPv6 network. So, you generally subnet those networks into /64 subnets so that the assignment can be proper. So /64 somewhat is the standard for the Ethernet network. So to recap, BGP is all about prefixes. It communicates between the routers to announce the prefixes, helping to define the network boundaries and facilitate the routing across the internet. So you must be having a question. So how basically BGP works? So how does BGP deal with IP prefixes? As I mentioned, that BGP announces prefixes to its neighbors. So for example, let's say that on the left-hand side, this is me representing the DE-CIX Academy with an autonomous system number of 196610. So I announce a prefix to my neighbor. Okay. So my neighbor shown here in the green receives the announcement and notes that the AS 196610, that is the DE-CIX Academy, has announced this prefix. So the neighbor in the green re-announces this prefix to all of these neighbors. So the neighbor in the orange receives the announcement from the green neighbor and notes that the prefix was originally announced by DE-CIX Academy and passed along by the green neighbor. So this process continues with the prefixes being propagated via BGP across the entire internet. So usually each router keeps track of where these announcements are coming from and who has passed them along. So in this way, the neighbor in the orange in the previous diagram knows that the prefix from the green neighbor who it got from me only. The blue node is representing the DE-CIX Academy, and BGP ensures that every router in the network knows that the origin of the prefix and the path that it took. So next, let's take a look at a slightly larger network. So imagine we have two locations. One is Frankfurt and Australia, and assume that I am in Frankfurt right now, and I am announcing this prefix to all my neighbors. Okay, this is an example of a prefix, the IPv6 prefix. So when I announce this prefixes, my green neighbor receives them and notes that it came from me, represented by the blue node, and the green neighbor then re-announces these prefixes to its neighbors. So each network that receives these announcements keeps track of the where they came from and includes the information in the announcement. So as you can see from here, all the way the prefix got propagated to the Australia. So this process happens everywhere in the network, and each router remembers where it received the prefix from and adds this information to the announcement. So eventually we have what is called as an autonomous system path, that is the AS path. And to visualize this, imagine that the blue node on the right hand side, you can see that the blue node is me. That is the originator of the on the right handmost side, and the green neighbor receives the prefix and adds the information, and then the orange neighbor receives it from the green neighbor, and so on. So this forms the path of the network providers who have announced and re-announced the prefix. Okay. So to sum up, the key element of BGP is that it announces the prefixes and keeps track of who announces and re-announces these prefixes. So this tracking ensures that each router knows that the prefix knows that the path the prefix took through the network, and maintaining a record of the autonomous systems involved in the entire announcement. So again, BGP announces prefixes to its neighbors. So these neighbors do not find these prefixes by themselves. So they must be configured. So you have to configure actually BGP on your router and to specify who are the neighbors and to which ones to talk using BGP. Okay. So the key element here is that the autonomous system number. So each BGP speaking device is a part of an autonomous system. So when you think of a network or a provider, for example, in this case, DE-CIX Academy, even though we are very small, it has its own autonomous system and an AS number. So this autonomous systems are actually numbered, and this number is actually attached to the prefixes and are maintained as a part of the routing information. So instead of the color dots, you can say that your router uses autonomous system numbers, and the path this announcement take is recorded as an AS path. So to visualize this, just think of the previous example that we had, wherein on the right hand side on the slide also you can see that the blue node is the originator and the green node is the one who receives and re-announces the prefix, and the orange node does the same thing to its neighbors. So instead of colors or shape, this information is actually represented by the autonomous system numbers in the announcement. So the AS path actually shows us which autonomous systems have forwarded the prefix in the announcement, and the rightmost AS in the AS path is called the originator, which is the AS that originally announced that particular prefix. So we have used a new term here, that is an autonomous system number. So many of you people must be knowing what is an autonomous system number, but still I'll just go through it. So what does an autonomous system really mean? So autonomous system is basically a group of prefixes. So even if you consider, according to the RFC in the 1930, an autonomous system is a connected group of one or more IP prefixes run by one or more network operators with a single clear routing policy. And this definition is just about IP prefixes and routing policies, and not about any hardware or routers. So, however, to announce these prefixes, you would actually need a hardware. You can have one or more routers for making announcements of your prefixes with an autonomous system number. So these routers use BGP to talk to each other with their neighbors and have a autonomous system specifically configured that is explicitly unique to each and every network. So BGP speaking router is always a part of an autonomous system and has an autonomous system number. And ASN is a unique number actually that identifies your autonomous system number, like I said. So initially ASNs were 16-bit, meaning that the range was only from 0 to 65,535 possible numbers actually. So however, some of them were not usable, and this amount was not enough for today's internet, as obviously 65,000 networks is quite a small number. So then the system was changed to 32-bit, providing a much larger range of numbers. If you consider a 32-bit value, it's more than 1 hour of ASN numbers that you could get from it. And for BGP to work, ASNs must be globally unique, and for that reason, only 32-bit ASNs were introduced. And each ASN can be assigned to only one operator, and so this uniqueness means that someone has to manage these numbers, right? So there is INA to manage them. So INA is nothing but our Internet Assigned Numbers Authority. So INA oversees actually sees this distribution of this ASN, but delegates the daily management to the 5 regional internet registries that we all know. So in this small diagram, I will just show you what are the regional registries that we have. So RIPE NCC is for Europe. Then we have APNIC for Asia and Australia. Then we have AFRINIC for Africa. Then we have RIN for North America. Then we have LACNIC for South America. So depending upon your location, you would contact the appropriate regional internet registries to get your ASN. So next, BGP announcing prefixes. So let's see. So now we have AS numbers on autonomous system and prefixes, right? So we need to announce these prefixes to the directly connected neighbors. So as I mentioned before, BGP announces prefixes to its neighbor, but these neighbors have to be configured. So BGP does not find them automatically. Okay. So how does this work? So it's quite simple actually. BGP uses TCP to connect to its neighbor. So unlike any other routing protocols, BGP does not use its own transport mechanism. Instead, it relies on TCP to set up the BGP session with a neighbor. So if you consider TCP provides several benefits for BGP, like you have the reliable transport wherein the sender knows that the receiver has received the information. Then we have the flow control feature also, wherein the sender cannot send data faster than the receiver can actually handle. Then we have framing also, wherein TCP ensures that the BGP messages are delivered accurately. So by using a TCP, BGP can focus on the main task of routing without having to actually manage these aspects of the communication, and actually making this process straightforward and efficient also. So moving on to the next slide. So you can see that BGP actually works incrementally. So it uses add messages and withdraw messages to update to its neighbor. So when a BGP session is actually established for the first time, the BGP speaker actually sends everything it knows or it is configured to announce to its neighbor. So this is called as the full table, and this only happens once. So after that, all the updates are actually incremental. So there's an add message wherein if a BGP learns about a prefix, it sends an add message to its neighbor saying that, hey, I have a new prefix, so here it is. So automatically the immediate neighbor or the connected neighbors know that the one prefix is updated and it adds it to its BGP table. So another type of message that BGP uses is a withdraw message. So if a prefix is no longer valid, it sends a withdraw message saying that this prefix is no longer available or exists. So remove it from your BGP table. So as long as the BGP session is active and the BGP knows that the session is up, so it keeps on sending this keep alive messages periodically, and TCP takes care of the session management also. Okay. So as long as BGP session is established and the router assumes that the neighbors are in sync, meaning that every piece of information that has been sent to the neighbor has been received and is processed properly. So it functions pretty well. So this incremental update feature actually helps keep the traffic low and the CPU load also low on the receiving router as well. So let's go back to the autonomous system path. So here I'm that I am announcing that I am an ASN AS517 and that I am announcing a prefix. So I add my AS number to it, this path, and announce it to AS286. So like you can see, this is the prefix announcement that I'm sending right now. And I add my AS number to the path and announce it to AS286. So AS286 adds their AS number and announce it's to its neighbor, that is AS5669. So AS5669 announces it to someone else. So that the AS path is built with the originator, that is AS517 on the right hand side. You can clearly see here how the AS path is defined in this slide as well. The rightmost AS is the path of the originator. So in this example, it's clear that there are prefixes which were announced over from 566 from AS517 to AS286 to AS5669, and the AS path looks somewhat like this. The origin AS is always on the right hand side of the AS path. That is the originator AS, as you can see here. So BGP has more attributes just than the AS path. So these attributes are actually attached to the prefix announcements. So let's take a look at the different types of BGP attributes that we have. So the mandatory attributes that we have with the BGP announcement is the AS path, which is a mandatory attribute, and we have the optional attribute as well. So this can be included in the BGP announcement, but they do not have to be actually. It's an optional one. So an example of an optional attribute is the multi-exit discriminator. That's the MED value, which I'll explain it in the later slides. And these attributes can also be classified as transitive and non-transitive one. So transitive attributes are the ones that they stay with the prefix as it gets forwarded through the BGP network. So once it's added, that remain attached to the prefix to the destination also. And non-transitive attributes are the one. So these are added to the prefix but are not forwarded by the uh, receiver. So some non-transitive attributes are also kept within the autonomous system and do not cross the autonomous system borders actually. So how does all this work in the router? So here is a simple overview that you can see in the slide, that router has several tables, including the BGP table and the routing table. So BGP operates in the BGP table where it receives the information about the network prefixes. Then the BGP might receive the same prefix from multiple neighbors, each with different attributes. So to handle this, BGP needs to select the best out of the multiple versions that it has actually received. So the BGP best path algorithm is used for this purpose, and it picks the best prefix and moves it from the BGP table to the routing table. So the routing table is then used to make the forwarding decisions. So I'll explain the best path selection algorithm in the next slide. So in this diagram, as you can see, that the prefix information is received, it's processed in the BGP routing table, then the BGP forwarding decisions are made and it's introduced in the routing table, and the routing table then moves it to the forwarding plane, and then the packet has been forwarded. So let's move to the BGP best path selection algorithm. So why do we need something like this? So when BGP receives any multiple announcements for the same prefix from different neighbors, the router needs to decide on a single path to include in the routing tables. It cannot have two paths. It has to be one best path in the routing table. So if it didn't, the router wouldn't know which path to use, so leading to confusion. So you want to have only one best prefix announcement to be selected. So this selection also isn't random, and it's based upon specific BGP attributes that I have discussed before, and the decision uh, process must be deterministic, meaning that the algorithm should consistently produce the same result even when given the same conditions also. Okay, so some of the criteria used in the selection process might seem old or outdated also, considering BGP is a very old protocol, but it is still being used as a legacy rules also. So these rules remain in place and they don't cause any harm. So even if they are a bit out of date as well. So let's break down to how BGP best path selection algorithm actually works. So let's get started with this. So let's take a simple example here. Imagine you have a network with two upstream sub providers on the left hand side, and on the right hand side, a prefix is being announced. Okay, so in this case, a prefix is being announced. So you receive two announcement for the same prefix, but from a different neighbor. Okay, to AS64500. So now you have to decide which path to choose. So to do this, you look at the AS paths and count the number of the AS numbers in each path. So for instance, if one path has three AS numbers, uh, and the other path has two AS numbers, so BGP will consider the shortest AS path as better. So in this case, the path with the AS path length of 2 will be chosen over the one with which is having the length of 3. So as you can see here, the on the left hand side, AS64500 has two routes installed in this routing table, wherein one is having 2 hops and one is having 3 hops. So obviously, the one with the shorter AS path length would be considered. This one is the better path, the one highlighted in yellow. So this brings us to the next part of the BGP best path selection algorithm, and that is the AS path length. So the general rule here is that the shorter AS path is actually considered than a longer one. So let's take a look at an example network again. So you have two paths, one with a shorter AS path, one with a longer AS path. Okay. And the important thing to notice is that BGP doesn't care about the geographical distance or the latency of this path. So BGP only knows that how many AS numbers are there in the path, and this is the only dynamic criteria that BGP is using at the moment to make the decisions, the AS path length. Okay. So, however, remember that the shortest path isn't always the best in terms of the performance, but it's the only information BGP uses it to decide. So now we add a third announcement, for example, one that goes through internet exchange, that is DE-CIX in this case, and this is a new path that has the same AS path length like the another existing path. So we face a situation wherein BGP must choose between the two paths with the same AS path length. Okay, like you can see here. So in such cases, BGP will try to rely on the other criteria to determine which path is the better. So in this case, if AS path length is same, then we'll move on to the next attribute. So if you believe that peering is better than upstreams, you must configure BGP to always prefer peering using the first tool in the BGP best path algorithm, that is the local preference. So in BGP, the path with the higher local preference value is actually preferred. So let's look what is local preference. So local preference is actually a BGP attribute that helps determine the which part to prefer in an autonomous system number. Okay, it is a 32-bit integer value, meaning that you actually have a lot of headroom to assign different values that you want. So the higher local preference values is the more preferred the path. Okay. So if a prefix in this example, if a prefix comes from a customer, you might assign it with a high local preference value that something like 10,000. And for prefixes that you receive from a peering partner, you can use a local preference of 1,000. And for prefixes you have from an upstream provider or a transit provider, you can use a much lower local preference value like 10 might be assigned. Okay. And I would request that you should avoid using the default value, like many routers have a default local preference value that is often 100. So if you see that this is the default value in the BGP table, it means that the prefix has already been altered when received. So to avoid confusion, it's best to use numbers other than the default values that you have on your router. So setting local preference according to your own convenience. So the next BGP attribute that we are going to look is our origin type. So this attribute is bit historical, but still plays a role in the determining the best path. So what is an origin type? So origin type is actually an attribute that tells you how a prefix was actually introduced into the BGP. So there are three possible uh, values for the original type. One is IGP, that is the Interior Gateway Protocol. So this value indicates that the prefix was introduced into the BGP via a network statement in the router configuration. So essentially, the prefix was added directly into the BGP by the originator. So this is by far considered as the most reliable type. Then we have the EGP. So EGP is actually a predecessor to BGP and hasn't been used actually for more than 40 years now. So if you see that there is an EGP value in the BGP table, it's a sign that something is unusual happening and it's not normal value for the modern day networks. Uh, then we have the incomplete value with a question mark. So this value actually indicates that the prefix was redistributed into BGP from another routing protocol. So the question mark means BGP doesn't know the exact origin of the prefix because it was handed over from some another protocol. Okay, so this is actually less reliable than IGP, but it is still in use. So the importance of origin type, if you ask me, is that while it's an attribute and is a part of the BGP selection process, but it's not a major uh, factor in considering the modern networks. So the presence of IGP over incomplete is common, while EGP is rarely used and is also a red flag. It shouldn't be actually be showing as EGP. Okay, so the origin type is also evaluated in BGP. It's often less influential compared to the other attributes like the AS path length and the local preference that we already talked about. So moving on to the next slide. So let's look at a simple network example over here. So imagine that there are two providers. The provider on the right is the AS64996 is a transit provider, meaning that it helps deliver to traffic to its customers. And the provider on the left hand side with the AS64500 is a customer of that transit provider. So these two providers are connected by two circuit, okay, a main circuit and a backup circuit. And the transit provider wants to ensure that a customer prefers the main circuit for the regular traffic. So to control which circuit the customer should prefer, BGP uses a mechanism called as the MED. MED is nothing but it stands for multi-exit discriminator. So MED is the step in the next step in the BGP path selection process and helps influence the decision on which the path to choose when multiple options are available for the customer. So MED is a value used for BGP routing uh, and is used to influence the choice of paths for the multiple options that are available. So MED comes into play when BGP receives two announcements for the same prefix, where the local preference and the AS path are actually identical. So, however, MED is only compared in the announcement coming from the neighboring AS, even if they are coming from different routers within the same AS also. So as you can see, MED is a non-transitive attribute, meaning it doesn't get passed beyond the immediate neighbor. So if you want to adjust the MED values using filters in your routers, the primary purpose of MED is just to signal to your neighbor that which path you have to prefer for a particular prefix. Next up, we have the BGP best path algorithm that involves our hot potato rules actually. So specifically, this is the step 6 and 7 of the best path selection algorithm. Okay. So this ensures that the traffic exits your autonomous system as quickly as possible using the nearest exit point. So in this example, if you consider, the rule clearly states that if a router receives the same prefix from both the external eBGP and the internal iBGP, it should prefer the one received via the eBGP peer. So for example, imagine a router at the bottom of the network diagram that learned the same prefix through iBGP also. Okay, so all the BGP attributes like the AS path, the MED, the local preference are the same in this in both the cases. So the deciding factors becomes how the prefix was being learned. So since the prefix was learned via the eBGP, so it is preferred. The router will choose that path. So this preference actually ensures that the traffic exits your network as soon as possible, rather than being routed internally and then diverting it to the transit provider. Okay, so this idea is to offload the traffic as quickly as possible and reduce the internal load also onto your network, the routing load I'm talking about. So see in this example, it was learned via eBGP. So the eBGP wins rather than the one learned via the iBGP. So One more case on the BGP route selection of the nearest exit. So if we add more routers to this scenario, BGP continues to prioritize the nearest exit for the traffic. For the example, the top router will send the traffic through the top connection, while the bottom router will send the traffic from the bottom connection. So this approach actually ensures that the nearest exit is already chosen and minimizing the internal routing of the traffic within the network. So the BGP's decision making process follows a sequence of steps starting from the top list, then on its way working down, and the algorithm checks for various criteria. First the local preference, then the AS path, then so on and so forth within the process. And ultimately in the step 6 and 7, which involves the nearest exit, which is also called as the hot potato routing, which are considered only if the criteria doesn't uh, have a result in the earlier choices. So next up, in the 8th point, we have the age of the route attribute also. So in step 8, in the BGP decision making process is about the age of the router, which can be a bit tricky to understand actually. So according to the Cisco's documentation, actually, this rule is when both the paths are external, prefer the path that was received first. So this rule actually applies when a router has multiple external BGP connections to the same outside destination, which often happens when connected to internet exchanges. So here exactly I'll show you how it works. So if a router receives the same prefix through the different external BGP sessions, so it will prefer the one that was received the first. So in the preferred connection, if the preferred connection which is up goes down, then the traffic will switch over to the other connection. So however, when the original connection, even if it comes back again, the traffic does not automatically switch back unless and until you have specifically configured some values like local preference or other settings to it. But in general use case scenario, even if the primary link comes up, the traffic won't shift to it. The reason behind this behavior is to maintain the stability. So if the connections are unstable and causing traffic to constantly switch back and forth, so it would create what is known as route flapping. So route flapping is actually not good, leading to network instability. So by keeping the traffic on the backup connection, even if the primary connection is restored, BGP ensures that there is a more stable network at the moment. So in the final step, in the step 9 and 10 of the BGP decision making process, if no clear decision has been made even after evaluating all these 8 criteria, the algorithm falls back to the two last resort rules, that is the router ID and the neighbor IP address. So here how it works. So actually, in this scenario also the lower value actually wins. So the router ID with the lowest router ID is preferred. So and if the neighbor IP address router ID are the same, then the path with the lower neighbor IP address is chosen. So these rules are actually designed to ensure that the decision is made even if the factors are equal. Okay. So however, it is important to note that these steps should be relied upon, but typically the decision should have made in the earlier procedure itself. If you find yourself that relying on the final step to influence the traffic, you should actually look at your BGP configuration, because something or the other is not proper in your configuration, because you should actually not fall off to this 9th and 10th step actually. This is the last resort actually. So there are some try optimizing more meaningful attributes like the local preference value or the MAD value or the AS path length. So this adjustment will have more substantial impact on the traffic patterns and the network performance rather than you being relying on the router ID and the neighbor IP in the last step. So let's go back again to the summary of what the attributes we discussed till right now. So let's walk through the BGP bus path algorithm step by step, highlighting each and every rule in a straightforward way. So the next hop reachability attribute. So if the next hop of a prefix is not reachable, BGP will discard the prefix announcement. It's the first check, ensuring that the route can actually be used or not. Then second, we have the local preference value. So this is the big rule at the start. So local preference is the value you set in your router to influence how the traffic flows. It's usually configured at the network entry point where you receive the prefixes. So you can use it to force the traffic to take a specific path if you don't set different local preferences value, then the next criteria is evaluated. So for example, I can give you a local preference example, like you have two service providers wherein you consider Airtel and Tata. So you have one exit path influenced from a higher local preference value. So if that goes down, automatically it falls back to Tata as your secondary connection. But when the primary connection of Airtel comes out, automatically the traffic will be rerouted via Airtel as you have set the higher local preference value. Then you have the AS path length. So BGP looks, this is the third step in the BGP path selection attribute. So BGP looks at the autonomous system numbers in the path and chooses the one with the shortest path. So this helps BGP to select the most direct route. So then we have the origin type. So this is a historical rule, like I said, it checks for the prefixes, how it got into the BGP, and it prefers the IGP over EGP and over incomplete value. Then we have the MED value. So MED is used when you want to enable to signal that you prefer this particular path for a particular prefix. Then a lower MED value is better. And note that MED is only compared between two announcements if the next hop AS is the same. Next, the sixth point is the eBGP and iBGP, and nearest exit point, that is also all these three attributes we call the hot potato routing. So these rules actually ensure that the traffic leaves your network as quickly as possible. So if the route was learned via eBGP, so it is preferred over iBGP, and the traffic exits your network to the nearest point, so minimizing the internal network forwarding as well. Then we have is the age of the route. So this rule ensures stability. So if the path becomes unavailable and traffic shifts to another path, so when the even if the original path comes back online, the traffic doesn't move back automatically. The older path with more stable route is generally preferred. Then we have the router ID and the neighbor IP address values. So if none of this previous step lead to a decision for the BGP route selection, then BGP look for a router ID or the neighbor IP address within the lower value is being preferred. And this is the last resort tiebreaker to ensure that the decision is ultimately made for the best path selection. So by following these steps, BGP actually determines the best path for routing the traffic. So now you can check your router's BGP decisions, and you can better understand why it particularly selected a route other than this one. Okay. So we have covered all the points here, the BGP attribute section. So thank you, everyone. So this was today's part of the topic.
Okay, so thank you guys for attending this session, and thank you, Apur, for this insightful and comprehensive session. I hope you guys found it interesting and educational. And I would like to remind you all that the learning has not stopped here, and our next session has been scheduled for 29th August. That will be led by Apur Torkar only. And I would like to request you to follow our social media pages to get an update on our new events and problem solving services. So once again, thank you and have a nice day.
If anyone is having any questions, they can ask. We are free for the questions.
Hello. Hello, Apu.
Yes.
Hello. Vishnu.
Yes, yes.
I want to know about BGP works on which layer in Wi-Fi? Transport or application?
BGP works on the network layer.
Network layer.
Yeah.
Okay.
BGP is a network layer protocol.
Because BGP use TCP port number 179.
Yeah, that's it is using just for the transport part actually.
Okay.
Yeah.
Okay. Thank you.
Hello.
Yeah, Swapnil.
Yeah, we can hear you.
Yeah. I just wanted to ask, how can we check the local preference in Huawei router? Recently, I have connected with D6. Earlier, I was having uplink with some local ISP over here, and still some traffic is going through that ISP only, even if we have directly bilateral BGP via you, but still some traffic is going from that uplink only. So I need to
So
check the local preference in BGP table, right?
Yeah, local preference is generally the same. If you have not explicitly set the local preference value in your Huawei router as well,
Uh-huh.
so it would be the default value only. Okay. So
Okay.
generally, if some of the traffic is via preferred via or transit links and not going via bilateral link, so you can
Mhm.
what you can do is apply an AS path prepend to your transit links. Okay. So that you have to take care first if you have applied that or not, because some of the times what happens is CDNs also find shortest hop via the transit link, so they can send a traffic via the transit links also. So when customers are connected to internet exchanges or peering partners, they usually have a higher cost set towards a higher AS path length towards the pairing partners. Sorry, towards the transit links, and shorter AS path lengths towards the pairing partners. So that you have to
Okay.
check in your configuration
Mhm.
if that is applied or not.
Okay. We have checked regarding this.
Yeah.
The path has been already prepended, but
Okay.
still causing same issue.
Then what sort of traffic they are using? You are seeing via the transit link. Have you done any packet capture for it? What sort of
No
traffic you are
packet
looking?
capture. Just one or two directly connected clients, means some IPTV providers are connected to your data center, and we had done bilateral pairing with them, but still it's not going through that path. It's going through my uplink provider only.
So in that case, actually, you have to take up with the provider itself how they are routing the traffic towards your ASN actually, because there is
Okay,
very
they
little.
need to do some configuration or
Yeah,
accept that IP pool.
yeah.
Okay, okay, we'll
Maybe
check
the
that.
maybe that pool that you are announcing via the internet exchange is actually not being able to serve that traffic via the exchange altogether. Because if you're even if you have done a prepend and if that traffic is being served to you via the transit link, that means altogether that route is not reachable only by exchange. That you have
Okay,
to make sure that it is reachable or not.
okay, okay,
Swapnil,
we'll check.
you
Yes,
can
sir.
just check a chat box for your for the command.
Okay, okay, sir. Thank you. Yeah.
PSPL.
Okay, you want our PPT, so no issues. We can share it to you. We are also seeing whether we could upload this data on the website as well on the academy section, so that people can download this webinar handouts also from there. No issue. We can share with you, Hemant. The next topic we'll cover some more part on the BGP and the second part on the 29th of August. So we hope everyone to see you again on that
Vasant.
session.
Hello, Vasant.
Yeah, Vasant, if you have any question, you can ask. Vasant is asking about a route reflector use actually. So that is a BGP advanced level topic, but still I will summarize it to you. Do we use a route reflector actually? So for instance, uh, you have, for example, a spoke router, and you have two different locations connected via IBGP. Like for instance, you have a Mumbai location, hub router, then you have a Chennai location, spoke router, then you have a Pune location. So what your Mumbai router basically will do is, if you set a route reflector client, so what it will do is, generally an IBGP rule is that it will not propagate the routes learned via IBGP to its internal IBGP peer. So whenever you configure a route reflector client to a specific neighbor, automatically the IBGP prefixes will get propagated to your IBGP peers as well. Just make sure that there are no routing loops happening. If those are diverse networks and those are just connected to the edge of the networks, you can configure it to as a route reflector client also. And where DE-CIX is also concerned, we also use the route servers as a route reflector client only. So we don't uh, route actually those routing packets. We just keep the routing information with us. The packets which are destined to the destination are forwarded automatically to the destination, to the specific ASNs that you want. Even if you are peer to the route service, we just make sure that package flow is proper. We just carry the routing information with us.
That if you don't mind the
People is
timestamp, will
asking
be
why do
also.
we use MD5 key in BGP? So that is also will be covered in the later stage, why authentication is used, why security is being used in BGP. Yeah. Navin will also share the PPT slide with you. The people who want the slides to be shared, they can put their email IDs in the chat box. We can share them by telling our marketing team. Yeah. No issue. We'll make sure that we have these handoffs uploaded on the website only so that people are able to download and watch the videos. I believe there are videos also on the website for the previous webinars where people can revisit and have a look and get understanding of the previous sessions as well. Thank you.
Sir, if you don't mind, to can speak in Hindi and explain the topic of route reflector in Hindi, if possible.
Yeah, sure, no issue, Amit. So basically, we do this webinars in Hindi because we have some South audience as well, and the North audience as well. So Hindi, they are not able to understand. Yeah.
No problem.
So route reflector client generally we use so that we know that we want to carry this information and just propagate to immediately to our iBGP peers rather than have some sort of another routing mechanism. So route reflector clients just takes the information from an internal iBGP peer and announces it to the another internal iBGP peer. So this generally is the rule of iBGP that whenever an iBGP peer announces a prefix, it should not announce it to the another iBGP peer just to avoid the routing loops. But if you have different networks separated with a spoke kind of a setup, so that usually doesn't have a routing loop involved in it. This just helps us with a lesser number of configuration also. You don't have to configure set of different rules. Automatically the routes are exchanged from one AS and propagated to another simply with the iBGP. Route reflector client doesn't have to be अमित हिंदी में बोलना था, मैं तो हिंदी में इंग्लिश में ही बात कर गया. दो नेटवर्क वहाँ पे एक्चुअली अगर होगा तुम्हारा एच पे, तो तुम्हारा कैसा रहता है, एक राउटर अगर कोई अनाउंस करे आईबीजीपी के पीयर्स से, तो दूसरे तरफ भी अगर उसको सेम प्रीफिक्स का अनाउंसमेंट अगर भेजना है तो तुम राउट रिफ्लेक्टर कॉन्फ़िगर कर सकते हो स्पोक में और भेज सकते हो आगे तुम्हारे राउट्स को. उसके लिए जनरली यूज होता है, सिंप्लीफाई करने के लिए होता है राउट रिफ्लेक्टर क्लाइंट्स को एक्चुअली. मतलब एक तरफ से राउट लेना, दूसरी जगह रिफ्लेक्ट कर लेना.
यस सर. और लूपिंग अवॉइड करने के लिए क्या करना पड़ेगा सर?
लूपिंग अवॉइड अगर करना है तो वहां पे राउट रिफ्लेक्टर जनरली यूज नहीं करना चाहिए. प्लीज गो ऑन म्यूट. जनरली कैसा रहता है, बीजीपी का मैकेनिज्म ही ऐसा होता है कि राउट लूप्स को अवॉइड करने के लिए आईबीजीपी का प्रीफिक्सेस को अनाउंस नहीं करता दूसरे आईबीजीपी के पीयर्स के साथ में. तो अगर तुमको राउट रिफ्लेक्टर क्लाइंट स्पेसिफिकली अगर यूज करना है इंटरनल बीजीपी में, तो फिर तुमको मेक श्योर करना होगा कि तुम्हारा नेटवर्क कहीं पे रिंग में क्लोजर नहीं हो रहा है दूसरे राउटर के साथ वापस फर्स्ट राउटर के बीच में. अगर स्पोक वाला तुम्हारा डिजाइन चल रहा है दो अलग डेस्टिनेशन के लिए, दो अलग राउटर के साथ और बीच में एक स्पोक है, तो आप राउट रिफ्लेक्टर क्लाइंट इजीली यूज कर सकते हो उसमें. हम लोग एक्चुअली यूज करते हैं एक्सचेंजेस में, लेकिन वो अलग चीज के लिए होता है. सीधा सीधा क्या है, कस्टमर का राउटिंग इन्फॉर्मेशन कस्टमर को मिल जाता है. हम लोग राउटिंग का इन्फॉर्मेशन सिर्फ कैरी करते हैं, हम लोग राउटिंग का कुछ प्रोसेसिंग करते ही नहीं है वो चीज में, खाली फ्लो मेंटेन करते हैं. एक्चुअल राउटिंग हम नहीं करते. ठीक है.
Yes sir, yes sir. Thank you so much sir. Thank you so much.
Okay. How to forward peering traffic in peering and not in telco. So peering traffic you have to forward in telco कैसे कर सकते हैं? अगर आपका बायलैटरल सेशन है, आपका डायरेक्ट पेयरिंग सेशन है, तो ऑटोमेटिकली ट्रैफिक वही से जाएगा, 90% ट्रैफिक वही ऑफलोड होगा. लेकिन फिर भी अगर टेल्को के पास जा रहा है तो इसका मतलब आपके पास आइदर बायलैटरल आपका एस्टैब्लिश नहीं है या डेस्टिनेशन प्रोवाइडर्स को आपका ट्रांजिट लिंक से जो है वो शॉर्टेस्ट पाथ मिल रहा है. वो आपको एक बार रीलुक करना पड़ेगा उसके लिए.
हेलो.
यस स्वप्निल.
हेलो. अभी जैसे आपने बताया कि टेल्को से उनको शॉर्टेस्ट पाथ मिल रहा है, बराबर?
राइट.
हाँ, तो सेम थिंग यहाँ पे हो रहा है. अगर उनको शॉर्टेस्ट पाथ वहां से मिल रहा है, तो उस केस में आपके थ्रू ट्रैफिक आने के लिए क्या करना पड़ेगा?
मैंने वो जैसे आपको बताया ना कि सबसे पहले ये देखना है कि एक्चुअल में हमारे से आपको ट्रैफिक वो प्रीफिक्स के लिए आ भी रहा है कि नहीं. अगर वो आएगा ही नहीं तो कितना भी आप प्रीपेड लगा लो, कुछ भी कर लो, वो ट्रांजिट से ही आने वाला है. सबसे पहले चीज आपको ये चेक करना है कि वो प्रीफिक्स जो आप चाह रहे हो वो डेस्टिनेशन को पहुंचने के लिए, वो पहले हमसे आपको मिल भी रहा है कि नहीं. ट्रैफिक रिवर्स में फॉरवर्ड तो आप चले जाओगे, रिटर्न पाथ आपको एक्सचेंज से आ रहा है कि नहीं, वो आपको पहले देखना पड़ेगा. डेस्टिनेशन के ऐसे अगर आप रिवर्स ट्रेस लोगे ना डेस्टिनेशन से, आपके प्रीफिक्स के लिए, तो आपको इजीली पता चल जाएगा कि आपका प्रीफर्ड पाथ कहाँ से आ रहा है, और एक्सचेंज से नहीं आ रहा है तो उसको इन्फ्लुएंस करने के लिए बोल सकते हो कि ट्रैफिक यहाँ से भेजो।
ओके, मतलब उनको ही वो रिक्वेस्ट डालना पड़ेगा।
हाँ,
ओके सर, थैंक यू।
जनरली ये प्रॉब्लम आकामाई के केस में होता है, या फिर
हाँ हाँ हाँ।
कभी, हाँ, क्योंकि कैसा रहता है, वो लोग जनरली क्या करते हैं, नियरेस्ट नोड से ट्रैफिक सर्व करने को देखते हैं। वो लोग ये नहीं देखते कि मेरा एक्सचेंज से कोई कनेक्टेड है या क्या आईएसपी से मैंने आकामाई का कैशिंग लिया हुआ है, ऐसा नहीं रहता है।
हाँ,
वो लोग नियरेस्ट नोड अगर रहेगा, उसका लेटेंसी अच्छा रहेगा, आरटीटी वैल्यू अच्छा
उधर
रहेगा,
से।
तो वहां से दे देगा ट्रैफिक। मैनुअल
ओके।
इंटरवेंशन, उन लोग ने मैनुअल मैपिंग बंद कर दी है। तो हम लोग ज्यादा से ज्यादा क्या कर सकते हैं कि हम लोग अपने डीएनएस पे आपका डीएनएस के पूल्स को अनाउंस करते हैं, अनाउंसमेंट को थोड़ा सा लंबा पाथ लगा देते हैं प्रिपेंड करके, ऐसा कुछ करके देख सकते हैं, थोड़ा ट्वीक
ओके।
करने के लिए, वैसा।
ओके, थैंक यू।
क्यों? So if yes path length are the same, the route goes from which path? If yes path length is the same, automatically अगर आपके पास दो पेयरिंग पार्टनर्स है, फॉर एग्जांपल आपके पास गूगल का दो लिंक है और आपका yes पाथ भी सेम है, प्रीफिक्स जाने के लिए भी पाथ सेम है, तो क्या करता है, ट्रैफिक कभी कभी लोड बैलेंस होके भी चला जाता है उसमें, इफ एवरी अदर थिंग इज सेम। दैट डिपेंड्स अपॉन द डेस्टिनेशन सिस्टम्स ऑल्सो, हाउ दे वांट टू राउट द ट्रैफिक। गूगल जनरली उनके केस में ट्रैफिक को ऑफलोड करके भेजता है, फेसबुक पे आधा आधा ट्रैफिक ऑफलोड करके भेजता है। डिपेंड्स अपॉन द डेस्टिनेशन प्रोवाइडर, हाउ दे वांट टू सेंड द ट्रैफिक। आईएलएल के केस में ऐसा होता नहीं है, आईएलएल के केस में एक तरफ से आने को देखता है ट्रैफिक, कुछ ट्रैफिक आ जाएगा, कुछ ट्रैफिक नहीं आएगा, वैसा हो जाता है। वो केस में आपको यस पाथ का प्रीपेड लगा के इन्फ्लुएंस करना पड़ता है ट्रैफिक को। और एक बार जो भी हमारा सोशल मीडिया का लिंक्स है, या फिर हमारे वेब पेजेस है, या जितने भी हमारे ट्विटर हैंडल्स है, इंस्टाग्राम पे, फेसबुक पे, लिंक्डइन पे, तो अटेंडेंस को रिक्वेस्ट है कि उसको लाइक और फॉलो कीजिए, तो आपको अपडेट्स उस पे मिलता रहेगा, हमारा क्या नया नया डेवलपमेंट्स है वो आपको, उसके बारे में आपको पता चलेगा, हम लोग का एडवांसमेंट्स क्या है। क्वेश्चंस कुछ रहेगा तो वो आप डाल सकते हो वहाँ पे, तो उस पे भी हम आंसर कर सकते हैं, आपको कुछ क्वेरीज है तो फेसबुक, इंस्टाग्राम, ट्विटर, लिंक्डइन, यहाँ पे हमारा मार्केटिंग टीम और हमारा टीम बहुत एक्टिव रहता है। थैंक यू एवरीवन। So I believe there are no more questions, so we can conclude this session. Thanks. Thank you everyone.
Thanks, everyone.
Thank you.
Thank you for watching.